Hello, everyone, and welcome to SIG Scheduling Deep Dive. I'm Bobby Salamat. I'm here with Jonathan Basseri. We are both software engineers at Google. I'm also a co-lead of SIG Scheduling. Today, we are going to talk about some of the features of Scheduler and also give you a general idea of what a scheduler is. Hopefully, these features are going to be useful for you if you plan to run medium to larger scale workloads on Kubernetes. So with that, let's take a look at what Kubernetes Scheduler is actually doing and what it is. So Kubernetes Scheduler, like many schedulers in many other cluster management service or software, is responsible for placing pods on nodes. During that process, it's actually uses various information, and it uses a centralized architecture. So in a centralized architecture, actually Kubernetes Scheduler must know about everything in the cluster in order to make scheduling decisions. So one option to know about everything in a cluster is to go and ask from an API server to give it all the information. But it cannot be done for every single pod, otherwise performance would be very, very low. So what it does, in fact, is that it caches a lot of information about the state of the cluster. And in order to keep this cache up to date, it relies heavily on the events that it receives from the API server. So it receives events for new pods, new nodes, changes in the pods, or changes in the nodes, or resources, and many other things in the cluster. So those events are a key part of the whole architecture of scheduler, and it's one of the few components actually in Kubernetes that relies heavily on events and never resyncs its information with the API server. Now with this cache, when a new pod arrives, the scheduler has to make decisions. So all these pods usually go to the scheduler queue, and scheduler picks one pod at a time. At least that's what it does today. It might change in the future, but that's what it does today. It only picks one pod at a time and tries to find a proper node for that pod. When it tries to find that node, it goes through several stages or several steps. The first one is to do a feasibility check of those nodes in the cluster. In the feasibility check, it actually tries to filter out the nodes that are not possible candidates for running the pod. Right, so for example, in this slide, node 1 and node n are not possible candidates. Node 2, 3, and 4 are possible candidates. So it filters out the rest of the nodes and focuses on the nodes that are feasible for this pod. And then in the next step, it tries to find the best node among these possible candidates. So this is step, in Kubernetes scheduler jargon, we call it like priority functions. It runs a bunch of priority functions. This is a little bit of unfortunate naming because priority can be confused with many other priority in a system. Like pod priority is another concept which is completely different thing. It has nothing to do with these priority functions. It's essentially the priority functions for us do ranking of these nodes. And in the process of ranking, scheduler tries to find the best node to run the pod. An example of these rankings is that, for example, which one of these nodes has the largest number of images that the pod requires? Or depending on the scheduling policy, it may use like best fit or worst fit to find the node that is better for running the pod. So among these three nodes that we have in this slide, node 3 happens to have the highest score. So scheduler will choose node 3 for running the pod, right? And then it goes to the last step of the scheduling, which is actually binding of a pod to that node. In that process, scheduler doesn't do a whole lot other than updating pod spec with this node name. And what happens at that stage is that API server sends an event to the corresponding kubelet on that node and tell that kubelet that you have a new pod. Now kubelet goes and does its own checking, and if it finds the pod as a possible possible candidate for itself. You know, there are checks that could fail, and kubelet could reject this pod. But if the checks pass, then the kubelet starts running that pod by preparing its containers and stuff like that. This is a pretty high-level overview of what a scheduler does when it tries to schedule a pod. With that, I'm going to hand it over to Jonathan to talk about some of the features of Kubernetes Scheduler that may be useful for you if you run any production workload on Kubernetes. And then later on, I'm going to talk about some of the more advanced features and give you an overview of the roadmap ahead. Jonathan, please.
Hi. So we don't have a lot of time to get through a lot of these features. We might not be able to go into the level of detail that we wanted to go into. So in the top corner, we've left links, and the slides are on the schedule, to all of the documentation for these features. And we'll try to leave time for questions at the end. Or find us and talk to us in person or on Slack. Several different scenarios that you can use the scheduler to solve. One of the simple ones, before that, we need to talk about how most of these features work. So you're probably familiar with labels. These are key value pairs, arbitrary key value pairs that are on any API object. You can use them to identify these objects, and then you can query the API server to get a specific set of those objects. So in all of these diagrams, we use these circles with gears to represent pods. So in this example, we have 4 pods. All of them have the label app equals my app, but they have these phase and role labels that are different. So if you were to query pods with app equals my app, you would get all 4. But if you say app equals my app and role equals FE, you would only get these 2. So given that, how could we target a specific set of nodes for your pod? So we have something called node affinity, which uses one of these selectors to get a specific set of nodes. So in this case, we require that our pod will run on a node that matches this label selector. So when we talk about filtering out the nodes, node 1 would get filtered out as not a viable candidate for this pod to run on because it doesn't have zone central. Sometimes you have related services that you want to run with each other. So for that, we have pod affinity. Pod affinity is a way to say, in this case, our service A wants to run close to a pod with the label service B. And what do we mean when we say close to is defined by this topology key. When the topology key is zone, we say we want our service to be in the same zone as any pod with label service equals B. So here we can see that the central zone has service B on node 2, but node 2 is out of resources in this example. And so node 3 is in the same zone, and therefore the pod can be scheduled.
Are there any standardized topology keys?
So the question was, are there standard topology keys? The answer is yes, and so the full name is actually like kubernetes.io/zone. They are, I'm pretty sure, in the documentation, but and one of the other ones is in this next example. You could specify host name, which means I want to run on the same node as. Now in this case, there's only one service B, and that node doesn't have any resources, so our pod cannot be scheduled here. So instead of specifying this as a hard requirement, it can also be specified as a preference. And so what you can do is this actually uses both to say that our service requires to run in the same zone as service B, but we prefer to run on the same node as service B. And since we cannot schedule onto the same node as service B, at least we can be in the same zone. So another type of affinity is pod anti-affinity, and this causes pods to be scheduled away from each other. The topology key is the same concept. So here we're saying I want to run my service on a node that does not have any pod with service equals A. And you'll notice in this example that service equals A is also on our own pod's metadata. So this is a self-reference saying, I don't want 2 instances of my pod to run on the same node. And this is useful for something that you really want to load balance and not have double the traffic going to one node. But you might still run into the case where a pod becomes unschedulable because of this, and so this can also be set as a preference instead of a hard requirement. And the other important thing to note is that pod anti-affinity is symmetric, so a pod which is already scheduled on a node can affect the scheduling of other pods onto that node. So in this example, we have a pod running on node 2 with anti-affinity against any other pod that doesn't have user equals A. So this is kind of double negatives, but so the pod that is user A here is saying, I don't want any pods on this node with me unless they also have the label user equals A. So this user B pod with no affinity spec at all cannot be scheduled on node 2. And I think I will hand it off to Bobby to talk about some other ways of scheduling.
Sure. So some of the features that you heard about are useful in many scenarios and for many production workloads. Some of the features that I'm going to talk about are probably more interesting for a smaller group of people, those who may probably run larger clusters. One of those features is actually taints and tolerations. Taints and tolerations, we use them for various things inside Kubernetes, but one of the interesting examples when it comes to scheduling is actually to save some of the nodes that have a special hardware for pods that actually need those special hardware. In a heterogeneous cluster, let's say, you have nodes. Some of them have, for example, GPU in this example, and some of them don't. Right, so a new pod arrives, and the pod only requires 4 gigabytes of RAM, let's say. All of the nodes in our cluster have 4 gigabytes of RAM. Only the first one, node 1, has GPU. So scheduler, if there is no particular preference, may happen to choose node 1 for running this pod, right? And then a second pod arrives a second later. This pod requires 4 gigabytes of RAM, but it also requires 1 GPU. So since the node with GPU is already used for running a pod that didn't actually require a GPU, we will not be able to schedule this pod at all. So this pod is going to remain pending. In order to avoid this scenario, we can taint that node with GPU with a special taint, or it actually could be any taint. This is like an arbitrary key value pair that you can put on that node and say, for example, key is GPU, and I want this to be saved, preferably only for pods that require basically GPU. So here we actually set the effect as preferred block scheduling. We have different effects. For example, one can be no scheduling, which means that only the pods that actually have the proper toleration can be scheduled. But in this case, we are just saying that we prefer no pods to be scheduled on this node. So a node that a pod that arrives and needs 4 gigabytes of RAM is preferred to be scheduled on node 2 or node 3. If they are full, we will schedule it still on node 1. But since these nodes are available, now we schedule that pod on, let's say, node 2. And now when that new pod arrives, which requires actually GPU, since there is no other choice for the scheduler to pick, it actually picks the first node. Sometimes you may want to have higher guarantees. In that case, you may go and actually put the effect as block scheduling or no schedule. In this case, the scheduler picks that node only if the pod has the proper toleration. So in this case, we put the toleration on this pod that requires the GPU, and scheduler picks that pod, picks this node with GPU for scheduling. One thing that I would like to add here is that there are ways to add these taints or tolerations automatically. So, for example, you can have an admission controller in Kubernetes that looks at the resource requirements of that pod and adds the proper toleration to the pod automatically. You don't need to always do it manually. But it also can be manual. So if you're creating a deployment, you can put this toleration in the template of the pod. And another feature is actually, which we've added recently, is priority and preemption. One of the main costs of a cluster is actually the amount of resources that are used in a cluster. And those resources are usually directly correspond to the number of nodes or amount of resources available on the nodes. So a way of saving money in a large cluster is to raise the resource utilization of each individual node in the cluster. This feature that I'm going to talk about was one of the most important features that helped Google raise resource utilization in Borg, in Google internal clusters, basically. In a cluster that all the pods have the same priority, when the nodes are full and a new pod arrives, the pod cannot be scheduled anywhere. But how do you specify if some of these pods are more important than the others? For example, you may run your CI/CD along with your production workloads in the same cluster. Why would you do that? Because you want to raise resource utilization in your cluster. But how do you specify which one is more important? That's how you put actually priority on your pods. In this case, let's say that the pods with, like the red pods have the highest priority in your cluster. The orange pods are medium priority, and the green pods are the lowest priority pods. All right, so you can put all of them in the same cluster. Now, a pod with highest priority arrives. The cluster is full. Scheduler will never try node 3 because it's running also a high priority pod. The scheduler never preempts a pod with the same or higher priority. But node 2 and node 1 are possible candidates for running this high priority pod because they are running pods with lower priority than this one. Scheduler looks at these two, and it has various metrics. But since node 1 has the lowest priority pods, that if removed can give enough resources to the scheduler to schedule this high priority pod. Scheduler deletes those two pods, or in our terminology, preempts those pods, giving them their graceful termination period. And after that graceful termination period expires, those pods are actually removed. And now this higher priority pod can be scheduled on this node. So why does this help with raising utilization in your cluster? So a lot of users today, in absence of priority and preemption, use a single workload or equally important workloads in their cluster and rely on cluster autoscaler to scale up the cluster when there is demand for more resources. But an alternative is to actually combine various types of resources so that when there are available resources, you run your lower priority tasks. And when there is a need for more resources for, let's say, your production workloads, you remove some of those lower priority tasks, which sometimes we call them like filler tasks, from your nodes and use the resources for running your production workloads. This is also helpful if there is a sudden spike in the traffic of your cluster. For example, suddenly there is a news about your website or your service, and people jump on their computers and want to check out your website or your service, and suddenly there is a huge spike. So if you have a lot of available resources used for, let's say, training your models, or I don't know, your CI/CD pipeline, then the scheduler can react very quickly and remove some of these workloads from your cluster and use it for running your more production instances of your web server or whatever the service you're running. Autoscaler can help as well, but autoscaler has to first detect the increase in the spike in the cluster and add new nodes, which usually takes minutes. So autoscaler has a little bit higher delay, and that's why priority and preemption can help you in this case. That's all of the features that we wanted to talk about today. And in terms of roadmap ahead, priority and preemption has existed since 1.8. It is still an alpha feature in 1.10, which is the current release of the scheduler. We plan to move it to beta, which means that it's going to be available by default and enabled by default in 1.11, and hopefully if things go well, we can move it to GA in 1.12. Gang scheduling is another feature that which we're working on. We are hoping to have an alpha version of gang scheduling in 1.12. If you have feedback about how we should do gang scheduling, please send them to us. We are designing the feature these days, and we would like to hear as many feedback as possible. There are other performance improvements like equivalence cache that has been in alpha for a while, and we are moving it to beta in 1.11, which is going to be the next release. Affinity and anti-affinity has been a beta feature. Hopefully we can move it to GA soon. Tainting node by condition, this is actually another feature which uses taints and toleration. We are moving those to beta. Scheduling framework is a big effort that we are also working on. This is actually good news for those who run like custom schedulers in their clusters. We are planning to move scheduler from its current sort of like monolithic design into a more pluggable architecture so that various plugins can be added to the scheduler in an easier way and removes the burden of keeping your custom scheduler along with the default scheduler. And last but not least, I would like to thank our contributors who have contributed code from literally around the world, various countries in Asia, Europe, and American countries. I really like to thank them. Some of them are present in this room. Make sure to say hi. And these are the 3 key points from this talk. With that, we're happy to take questions. Yes?
You talked about the priority.
The mic.
And is there anything that you can intelligently reschedule the parts based on the workload demand? Like, because I co-lead one of the work groups in Istio. I give you an example of Istio, for instance. Istio mixer takes more resources as you load up and the more load come in. Right. So if there is a feature in the scheduler that can dynamically reschedule some of the parts which are overloaded, that will really help. Otherwise, right now, what will happen is because the mixer where the part with the mixer, right, it's there in the node, that node will become a bottleneck for rest of the workload parts.
All right. So basically, I guess you like to run all of your pods with the same priority, but you still expect some level of intelligence into.
Yeah, one way to do. I'm sorry.
You're saying vertical scaling.
No, yeah, it's actually like this, right? Let's say you deploy your application or Microsoft application, and then you have Istio service mesh deployed. Basically, all of pilot, everything's like a pod, right?
Sure.
So as you get more workload, as your workload is actually scaling out, right? And what will happen is you have some of your application pods and mixer sitting in the same work node. Same work node.
Suddenly, some of them
Suddenly
have
what will
higher
happen is
usage.
because mixer is taking more resources.
Right.
So the other application pod is not getting it, and that will be the bottleneck for your scalability.
Right.
So if the scheduler is intelligent enough to understand that bottleneck, and if you have resources in other worker nodes in the cluster, if it can dynamically reschedule them.
Right. So it's not exactly a scheduler, but Kubernetes in general is going to have a feature similar to what you're asking. Basically, autoscaler is going to actually, I guess, is having this feature in alpha, which is basically vertical pod auto scaling. It increases the amount of resource requirements for that pod that now has a higher usage. And we also have the scheduler, which is another incubator project. The scheduler also looks at the nodes which have, let's say, close to the capacity and removes some of the pods. And when the pods are removed, scheduler again schedules them elsewhere. So basically, a cooperation of various components in a cluster will result into the feature that you're asking. Yes. Yes.
I have a trio of related questions about scheduler capacity. Is there documented complexity of the scheduler? It looks like, from what you said, the cost of scheduling one pod is going to be order of n log n. So my question is that right, or do you have a different answer? And the related question is, I saw somewhere that there is a goal of being able to schedule, I think it was, I forget the goal, but is there a stated, documented throughput, achieved throughput on the scheduler?
Yes. So in terms of throughput, we do definitely have some consoles that actually you can go and look. There are like scalability team actually has these graphs that shows the scheduler throughput. But in terms of complexity, it's really, really hard to come up with a single like OAuth and login or anything like that. The reason is that it really depends on the features that, or scheduling features that pods request from the scheduler. So a pod that, for example, has interpod affinity, let's say, will go through more basically predicates that do more complex operations or computations in the cluster. And actually, that could have been a lot worse than n log n. It could be like n cube or something like that, right?
So I tried looking at the performance dashboard. I didn't find scheduler throughput on it. Where would I find it exactly?
I guess it's there, but I don't have any on top of my head any particular link. But I guess it's in the same performance dashboard.
The metric you're probably looking for, I think, is called scheduling end-to-end latency, and it's
Maybe
a histogram in Prometheus.
So I divide by latency to get throughput. 1 over latency mean throughput.
Yeah. Yeah.
But it also depends, it really depends on the size of your cluster as well. So those are all run with a particular cluster size and a particular number of pods in the cluster.
Yeah. Oh,
Go ahead, there's another question.
with the recent changes in kubelet eviction and implementing priority and preemption, can we expect quality of service classes to go away?
No, we're going to try to remain backward compatible as much as we can. But you're right, there is somewhat of an overlap between these two, but they are not exactly addressing the same problem, so they're going to stay. You can talk more about that offline, because I guess there has been a lot of discussions about that. Right.
So I wanted to follow up on the heterogeneous node scheduling problem, taking your GPU example. Can that extend to network capacity, to quantity and type of NICs and physical Ethernet ports? And can it extend to NUIOA awareness as well?
Yes, of course. Yes, you will have multiple options when you create, for example, nodes for your cluster. If your nodes have special hardware, you can taint them with various types of taints. The taints are pretty generic. These are just key value pairs. So Kubernetes is not going to do it automatically for you. It probably needs some level of coding on your side to add proper taints for the nodes in your cluster. But once you do it, yeah, it works pretty much for any type of hardware.
What about the NUIOA part? Like if I have, I want to put one pod on each of 2 sockets with awareness that the high-speed NICs are honed PCI-wise to individual sockets.
That I don't know the answer basically. What you're asking is very much node related. How node basically assigns these 2 ports to various pods in the cluster or on that particular node. And I don't know the answer. I'm not so sure if actually supported today, or if you can put that particular requirement in the pod spec. I'm not aware of anything like that.
Hi. The question I have is it possible, so currently the scheduler uses the number of CPUs in the machines, and in the pod spec it looks for the CPU request to find the available node, right? We wanted to basically make use of overcommitting, and not by using a limits on the request, just by in terms of scheduler bin packing more parts onto the machine and then the available resources. Is something community is looking for?
Yeah. So there are multiple ways of achieving that. One is to not to specify any resource requirements in your pods, right? So that's basically the best effort pods that we have in Kubernetes. And then scheduler assumes that your pods do not need any particular amount of CPU or memory, but they actually do. And once they are scheduled, they are going to be using some amount of CPU, and you will eventually achieve some level of overcommitment on those nodes. Another possibility is to actually specify lower requirements than the actual usage, and you can specify a higher limit. That's what we call burstable pods, essentially. That also achieves overcommitment of the CPU or even memory. But in case of memory, it's a little bit harder because we cannot really actually run more pods than the amount of memory that we have on a node. So you may end up having some of your pods killed. But CPU is a more like compressible resource, so it's easier to achieve overcommitment for CPU. Yes? No, not really. Not at least today. That's a completely different model as we have today. Well, the question is, are we ever going to consider distributed scheduling as opposed to the centralized scheduling that we have today? So that's a model that, for example, Mesos uses. And it's a different model of scheduling. We don't think that we are ready really to absorb all of the changes there. And it's a little hard, given that, that Kubernetes API has evolved over the assumption that we have a centralized scheduler. It's a little harder to come up with a distributed scheduler. Yes?
So yeah, let's say you have a certain type of pods that cannot be scheduled for some reason. Are these queued? Are these dropped at some point? So what is the expected behavior?
Right. So the question is that if there are many pending pods, when are going to if they're going to get dropped eventually, or are they going to remain pending forever, or what is the behavior? The behavior is actually Kubernetes scheduler keeps them all in the queue as long as they exist in the cluster. So if they are deleted at some point, they are deleted from the queue as well. But Kubernetes scheduler will keep retrying to schedule them until it actually can, or they are deleted. So in the newer architecture of Kubernetes, is essentially as soon as an event arrives that could possibly make those pods schedulable. For example, a pod is deleted from the cluster and releases some resources, so Kubernetes scheduler retries those pods.
I have a related question. So what I observed in my cluster is it's sort of extremely unfair. Like when it scales up, the last guy wins because there's an incremental backup. On the retry. So the last guy wins, and the guys because they are the longest, they sort of are the last ones to get scheduled.
Right.
My customers are so they get extremely annoyed when they doesn't get scheduled for that.
Right. So yes, so the question is, sometimes when a pod is getting retried a few times, the scheduler automatically applies a backup to that pod once the pod cannot be scheduled. And as a result, a pod that has been longer in the queue probably can take longer to schedule because of the backup time. So Kubernetes, the newer Kubernetes scheduler actually uses, it's a part of priority and preemption, which is not enabled by default, but the newer mechanism actually is sorting pods based on their priority. So pods with higher priority are in front of the queue. And today we don't have any backup mechanism for this newer architecture. We may add actually a backup mechanism for that as well to make sure we have a fair, we give fair scheduling opportunities to the pods in the queue. But anyway, the idea here is that the pods with highest priority get the highest chance of getting scheduled, and those with the lowest priority go to the end of the queue. So that behavior is going to change.
So we're at time, but we're both around for the rest of the con. Definitely find us and ask us more questions. We're on Slack, we're on email. Thanks for coming.
Thank you.